Hello friends, this is Professor Sundar Singh from Department of Physics, Bareilly College, Bareilly. As you all know that a very important term we usually come across in our daily life is KYC, that is know your customer, which is related to your banking operations. So in similar to that, belonging to physics fraternity, we come across several semiconductor devices and I thought that I must deal with the basics of some of these devices. So I have started a series on know your device, that is KYD, similar to KYC. So in this series I will start with the first device, that is basically the PN junction diode, which is a two-terminal semiconductor device having P and N type regions, and in between that there is a PN junction. This is basically a unidirectional device. That means the current conduction is only along one direction, and in the other direction the current conduction is very small compared to the previous direction. For this device to construct the suitable materials are germanium and silicon, as you all know, and their band gaps are roughly 0.7 electron volt for germanium and 1.12 electron volt for silicon. Now the question comes that why silicon is preferred for most of the semiconductor devices. It is because of its larger band gap, which results in the lower leakage current. So silicon has a 1.12 electron volt energy band gap between its valence band and conduction band. This larger band gap results in less number of creation of thermally generated minority charge carriers, which are responsible for leakage current. So because of that, leakage current in case of silicon devices is of the order of nanoamperes, whereas in case of germanium it is up to the order of microampere. So 1000 times higher is the leakage current in case of germanium PN junction diode compared to the silicon PN junction diode because of that. And secondly, the silicon diode can work up to the temperatures of 150 degrees centigrade to 180 degrees centigrade, whereas the germanium diode performance degrades above 75 or 70 degree centigrade. So because of these factors, silicon is mostly preferred for making PN junction diode. Now the important part is that what are the basic applications of this PN junction device. So basically here you can see that AC to DC conversion, that means you can convert alternating current and voltages to direct current and voltages. Here I have shown these conversions. These are the AC signals and these are the rectified or converted DC signals which have some amount of AC. And the another important application of PN junction diode is in wave shaping networks, that is in the clippers and clampers. So these clippers and clampers can shape the input waveforms and can give you the resultant output waveforms which can look like this. Another important application is in switching circuits. PN junction diode, as you all know, conducts only in one direction. It can work as a switch, and in that application it is basically working as it can be used in logic gates. It can also be used for the demodulation purposes. For it can work as a demodulator. It can be used as a envelope detector, and sometimes it is also used in protection circuits. The next thing is that two important parameters are depletion layer and potential barrier. Depletion layer is basically the very thin layer around the PN junction which is devoid of free charge carriers. It only contains fixed and immobile ions. So it is a free carrier free transition region. There are no charge carriers present in this depletion region or transition region. At within that depletion layer, the positive and negative ions give rise to a potential barrier, inbuilt potential barrier to exist at the junction, which is known as the potential barrier, which is about 0.3 volt for germanium devices and 0.7 volt for silicon devices. There is an important parameter which we will see in the IB characteristics also, that is the cut-in voltage, which is defined as the minimum forward bias voltage required to start significant current conduction. So when the diode is working under forward bias condition, then the minimum forward voltage applied to the PN junction, which causes the diode to conduct significantly, is known as the cut-in voltage. We will see in the IV characteristics also. Now the question is that how will you forward bias the PN junction diode, and what are the changes that occur during the forward bias. So basically, to forward bias a PN junction diode, what you do is to connect the positive terminal of the battery to the P layer or the P region of the diode, and the negative terminal to the N region. And in that situation, you will see that the diode conducts heavily and the current is of the order of few milliamperes, while in the reverse case, in which you reverse bias the PN junction diode, you have to connect P region to the negative terminal of the battery and the N region to the positive terminal of the battery, which causes the potential barrier height to increase, depletion region width to increase, and significantly lower current, which is basically known as the leakage current, that flows through the device, that is of the order of few microamperes. And that leakage current is actually because of the thermally generated minority charge carriers, so that is dependent upon the temperature of the device. Now here I have shown the characteristics of the PN junction diode. This first quadrant part is for the forward bias operation of the PN junction diode, and this is for the reverse biased operation of the PN junction diode. You can see that this very small leakage current is flowing through the device so long as the reverse voltage across the PN junction is kept below the breakdown voltage. And if you increase the reverse voltage higher than the breakdown voltage, then the PN junction diode will undergo in the breakdown mode, which is not the normal operation mode of the PN junction diode. Now this important parameter, that is the leakage current, is of the order of nanoamperes in case of silicon diodes and microamperes in case of germanium diodes. Now here is the point that I must emphasize, is the cut-in voltage. This cut-in voltage is basically the minimum forward voltage at which the conduction is significant in case of forward biased PN junction. Now this is basically the 0.25 or 0.3 for germanium devices and 0.7 volt for silicon devices. Here you can see that the current is exponentially increasing because of the carrier multiplication. So you can see that current is rapidly increasing. So when the diode is conducting under forward bias, then the voltage drop across it will be around 0.7 volt for silicon devices and 0.3 volt for germanium devices. Okay, so in normal operation, the diode is conducting heavily under forward bias and not conducting under reverse bias, so it can work as a switch. Now here I have summarized some of the things about forward and current reverse bias conduction of the diode, p-n junction diode. So these things I won't repeat now. Now here I have shown the resistance values. Here you can see that resistance, dynamic or AC resistance you can calculate, as well as you can also calculate the static or DC resistance. So under forward bias you can see that static or DC resistance is of the order of 10 to 100 ohms, whereas dynamic or AC resistance is of the order of 1 or 20 ohms. So you can see that 1 to 20 ohms. So you can see that AC resistance of the diode under forward bias is relatively smaller than the DC resistance under forward bias. But if you compare the resistances under forward bias and reverse bias, then you can see that there is a great difference between the values of resistance shown by the diode under forward bias and reverse bias. So here is of the order of few ohms and here is of the order of mega ohms. So 10 raised to the power 6 factor is here. So here you can see that the diode is almost non-conducting, and here the diode is almost freely conducting. Then we can see that the applications of bias diode, if you are biasing the diode, then the diode can be used as half wave rectifiers, full wave rectifiers, bridge rectifiers. It can also be used in battery chargers, DC power supplies, and as demodulators or detection of modulated signals. So you can see that because of forward resistance is extremely small compared to reverse resistance, the diode acts almost like a one-way switch, conducting in one way and non-conducting in other way. So it, because of this property of the diode, it can be used in rectifiers for the conversion of AC signals into DC signals. Okay, then next moving on to capacitance, is very important property of p-n junction diode is the capacitance property shown by it under forward and reverse bias. So now you can see here that two types of capacitances are shown by the p-n junction diode. Both are present under forward bias as well as under reverse bias, but in one case one of the capacitance dominates and in the other case the other capacitance dominates. Now when you are talking about the reverse biased p-n junction diode, then we will see that a capacitance known as transition capacitance or the depletion capacitance, mathematically given by this expression epsilon A over W, where A is junction area, W is depletion width. This capacitance, transition capacitance, is very important and it dominates under reverse bias. Now you can see that here a factor W is appearing in the expression, and that W is the depletion region width, which depends upon the amount of reverse bias applied to the diode. So you can see that if you increase the reverse bias, that increases the width of the depletion region, and as a result the transition capacitance decreases. So this transition capacitance is voltage variable capacitance. It depends upon the amount of reverse bias applied across the p-n junction diode. As you increase the reverse bias, the transition capacitance decreases, and this important capacitance property of p-n junction diode is useful in case of RF and microwave circuits. Now the typical value of this junction or transition or depletion region capacitance lies in the range 1 picofarad to 100 picofarad. Now the another type of capacitance is known as diffusion or storage capacitance, which is mathematically given by dq over dB. Now here this capacitance is present under reverse bias also, but to point the point to remember here is that this diffusion or storage capacitance denoted by CD is dominant under forward bias. So if the diode is working under forward bias conditions, then diffusion capacitance will dominate over transition region capacitance, whereas when the diode is operating under reverse bias, then the transition capacitance will dominate over diffusion capacitance. Now talking about this diffusion capacitance, this is basically caused by the injection of or storage of minority charge carriers. So the striking difference from that of the transition capacitance is that diffusion capacitance is based on minority charge carriers, whereas transition or depletion region capacitance is basically dependent on majority charge carriers. And the second difference here is that the value of this diffusion capacitance lies in the range 100 picofarad to 10 nanofarad. So you can see that this is quite large or compared to the transition capacitance. So diffusion capacitance is much larger compared to the transition capacitance. Here I have summarized these values and under what conditions which one of these capacitances dominates over the other. Now here I have listed some of the high frequency applications. So because of the property of capacitance shown by this PN junction diode, this PN junction diode is basically limited for some of the applications. Now high frequency applications, these are dependent upon the capacitive properties of the PN junction diode. RF tuned circuit, frequency modulators, satellite communication systems, radar receivers, microwave filters, voltage controlled oscillators. Now here these are the variants of PN junction diode. The ordinary PN junction diode, that is sometimes known as a rectifying diode because of its one-way conduction, is not suitable in all cases. So semiconductor devices or semiconductor diodes have been developed by modifying certain features of the original PN junction diode, and these modifications are basically guided by the applications in which we want the diode to work in. So because of that, I have listed here, I will not go into the details of these variants of PN junction diode. I will talk only a few things about these variants of PN junction diodes. So the original or the rectifier or the ordinary PN junction diode, which is made up of germanium or silicon, its symbol is shown here. This region is P region and this vertical region is the N region. This PN junction diode, rectifying diode, is basically have the ability of conducting high currents under forward bias and low current under reverse bias, and major use of this ordinary PN junction diode is AC to DC conversion. Now another variant of this PN junction diode is a heavily doped PN junction, which have a very thin depletion layer, and this is specifically used for its operation under breakdown mode or breakdown region, and useful for the applications of voltage regulation. So this variant is known as Zener diode, which is a heavily doped PN junction normally operated under reverse biased breakdown region. Then another variant of PN junction diode is the light emitting diode, which is specifically used for the purpose of light emission, for the emission of visible light or infrared light, meant to be used in displays and indicators. This light emitting diode, as the light is coming out shown by the arrows, and this light is coming from P region and this N region is here. So this light emitting diode is basically a forward biased PN junction diode, but for the purposes of emission of visible light we cannot use germanium or silicon materials. Other materials like gallium arsenide, gallium phosphide, indium gallium phosphide, etc. are suitable for the purpose of manufacturing light emitting diodes. Then another variant here shown here is the photodiode. Now in this case of PN junction, the light is made incident upon the junction, and this photodiode is basically a reverse biased PN junction, which basically works for the detection of light. So it is used in optical communication. Light is made incident upon this reverse biased PN junction. Another variant is a solar cell, which is mostly used for the purposes of solar conversion of solar energy into electrical energy. In this case, no external bias is required, so no, neither it is forward bias nor it is reverse biased externally. Bias is generated itself in this device. It is used for solar power generation. The symbol is shown here. So light is made incident upon this PN junction, and when the conditions are suitable, it converts electrical energy, solar energy into electrical energy. Now here is another variant of PN junction, which is known as Bayraktar diode, which utilizes the voltage variable capacitance property of the PN junction diode. So the PN junction is now here used as a voltage variable capacitor. This voltage variable capacitor or Bayraktar diode, whose transition capacitance is proportional to 1 upon square root of the applied reverse bias, is basically used the tuning circuits of most RF devices, radio frequency devices. Another variant, that is the Schottky diode. The ordinary diode suffers from the limitation of because of the presence of that depletion region or stored minority charges. This ordinary PN junction diode cannot be used for high frequency signal rectification. So to remove that limitation, if we have a PN junction of metal and a semiconductor, not the semiconductor on both sides of the junction, then in this case, as the metal do not possess any minority charge carriers, so here there will be no stored charges, no reverse recovery time needed, and in this case, this diode, that is a metal semiconductor diode, the hot carrier diode or the Schottky diode, will be suitable for the purposes of rectification of high frequency signals. This consists of no depletion layer. Now another useful variant of PN junction diode is that is a tunnel diode. This tunnel diode is basically based upon the tunneling of electrons from one side to the other side of the junction. When the depletion region width is small and the electric field at that depletion region or at the junction is high. Again, germanium and silicon are not suitable materials for the construction of tunnel diode. Gallium arsenide or some other materials, silicon is sometimes used, but gallium arsenide and other materials are preferred over the germanium, etc., for the construction of tunnel diode. So this tunnel diode is important because of a important feature of its characteristics, and that is the presence of negative resistance. In its IB characteristics, a part of the IB characteristics shows the decrease in current with increase in the forward voltage. So that means it shows a negative dynamic resistance, and the property of this negative dynamic resistance makes it useful to be used in microwave oscillators. Finally, I will come to the pin diode. That means there is an intrinsic layer between the two P and N doped layers. So this kind of diode or this kind of variant is known as the pin diode. It has an intrinsic semiconductor layer between one P region and one N region. This is suitable for radio frequency switches and attenuators. Now, so I have described here almost every aspect of the PN junction diode, which is a very common semiconductor two-terminal device used in several circuits, having two important features: that it is having one-way or unidirectional conduction. Secondly, it has very low resistance under forward bias, very high resistance under reverse bias, and thirdly, it shows capacitance properties Transition region capacitance or depletion region capacitance dominate under reverse bias, whereas diffusion capacitance dominates under forward bias. So these are some of the things that you come across, or that you want to study, or that you must know about a PN junction diode. Now in the end, I hope that I have covered most of the thing about this device. So in this know your device lecture series, uh, in the lecture 1, PN junction diode has been explored for some of its features and its applications. In the end, friends, I have listed here 4 important problems. If you cover these, I want that you must try to solve these problems. These are important problems and specifically useful for those candidates who are appearing, or who are targeting their competitive exams like GATE, NET, or some services like TGT and PGT exams, or assistant professor exams. So I will advise all those candidates to go through these problems and try to solve these problems, and the figures for these problems are given here. So you can attempt these problems and try to solve these problems. I hope